8.3 is then 8.4 is really simple. I think you learn about that. Suppose in quantum mechanics. I hope you learn about that because it's like a quantum mechanic problem. It's related to eigenvalue because if you have a operator and have eigenvalue that say h, you have the h operator on so a bunch of psi, whatever we call it, the phi sub n, it's lambda n phi. Assuming h is Hermitian, then this phi n, this is conic delta. You can always choose normalize your eigenfunction so that they are orthonormal. And for Hermitian operator, lambda n's are real. They're all real. Right? And for this the variation method to work is so n is obviously it can be infinite, and so you have this. You can start with any number actually, so infinity. So you have infinitely many of them, but assuming that it has a lower bound than n, so n or n will be larger, or greater or equals to any smallest of one, say, or n. So that so you have the lowest eigenvalue, or sometimes it reverse that you have a maximum, but you have no minimum. So that also works. So instead of getting a lowest energy state, that becomes a highest energy state. But anyway, you can. This is obviously interchangeable. So you just consider one problem. You have a minimum. Okay, and then the idea is any arbitrary state. So obviously, so any arbitrary state psi that there's a combination of this eigenstate, expand the state using eigenstate and mu. I think the textbook called mu. A sub mu, phi sub mu. Okay, and obviously then you can calculate the so-called expectation value h operates on psi, and then take the scalar product with psi itself. Right. And then just put it on this side, and you change the coefficient of complex conjugate, and then you have phi mu. And h operated on psi is h operated on all the eigenstate. So you have a sum over. Now you use another index for that. Nu and then a nu. When you operate on that, you get lambda nu. Okay, and then this phi mu nu, they satisfy the conical delta, and you can sum over one of the summation and get sum over mu a mu square, because one of them is a complex conjugate. So when you have complex conjugate multiplied by itself, you get the absolute value square multiplied by lambda. Okay, that because all of them are larger than lambda sub 0, you can say it's always larger than lambda sub 0 multiplied by this summation mu square. but that would be just one. This would be just one because this state is also normalized. When you take the psi, take the scalar product of itself is set to 1. Right? This is normalized. So when you do that, you substitute this into both of them. That is exactly this one. Sum over all the coefficients squared. So that is just 1. This is equal to lambda 0. So the expectation value is always greater than the smallest eigenvalue. Right? And so that's the idea. And now the equation that we need to solve is, I mean, what you want is your ground state, right? So you want to solve, supposedly, what you want to solve is h phi sub 0 equals to lambda sub 0 phi sub 0. You want to solve the ground state phi sub 0, but the h is a differential operator, right? And then sometimes the differential operator is too difficult to solve. You don't know what the exact solution of this differential equation. What you do is take an approximation to phi sub 0 h operate on phi a certain trial function. Let's use textbook symbol. I don't think has one. A textbook didn't write down the formula for that. But just because a certain function f as an approximation. So you want to solve it. That define a parameter. What parameter should we use? Zeta. I mean, the textbook doesn't have equation. You want to h operate on psi is roughly. You want to find a solution like that, right? But this is a parameter. It means that it depends on whatever parameter in h, like x or whatever, a differential equation in x, and it also depends on the parameter psi. Because see, no, the zeta depends on the zeta, right? And what you want is calculate your you have average. This your energy, or this is expectation of the energy, which is supposedly this h, right? You take the scalar product of F, h operate on F, and that obviously depends on zeta. After you integrate over x, right? This scalar product is integrating in x, right? And that becomes a function of zeta. And then you choose zeta such that it's a minimum, right? And you basically get the phi zeta, and whatever zeta you get, you evaluate that minimum, right? That is supposedly that will approximate this size of 0, phi sub 0, right? And so obviously that is not exactly phi sub 0, but what you want is maybe keep doing that. You keep refining a better F and so on, and so that you get the smaller and smaller values. So this E obviously, just from our discussion, this E is always E equals 100. So you keep choosing different F such that this E is as close to lambda sub 0 as possible, right? And that's the way to find an approximate solution for this ground state phi sub 0, right? So the idea is very simple, but the only problem is that's involved a integration. Your differential operator on your trial function and multiply by the function and do the integration. And you need to do the integration and then finally minimize that with respect to your parameter of your trial function. So that is an approximate method. Which is sometimes practical if your differential operator is too difficult. I think I'm just out of time. Okay. Any question about this? So it's so straightforward. Then there's a homework problem for this method. So you work it out. You should know how to do it. Okay.